All right, so let's start with where we left yesterday. So you remember we had this free electron parabola. And then we turn on the perturbation, and in the presence of the perturbation, what you get is something like this. And then you have the first zone boundary, second zone boundary, and so on. And the energy of the perturbed system does something like this. And the same thing on the negative side, which I'm not drawing. So these points are pi by A, two pi by A, and so on and so forth, 3 pi by A. And so So the white represents the unperturbed parabola, the free electron parabola, and the orange represents the parabola that you the changes that will occur because of the perturbation. And the perturbation here is in the form of a periodic potential. So your Hamiltonian now has a potential as well besides the kinetic energy term, and this potential obeys the lattice translational symmetry. Okay. We can also draw this slightly differently. Where we put everything in the first zone. So minus pi by A to plus pi by A. And using the reciprocal lattice vectors, you can bring these sections inside. Okay, this doesn't look good. This has to be at the same point. So. Yep. And then using the lattice vectors, G's, you can bring this section over here like this and this section over here like this. So it will be kind of, and this will be kind of. All right. So this section is here, and this section, this section is over here. And this way of drawing the dispersion is known as the reduced zone scheme, as opposed to this way, which is known as the extended, I believe, Now, depending on the number of electrons per lattice site or per unit cell, if you like, in our notation is the same because we're dealing with Bravais lattices. So, in today's lecture, what we have to show is that if you are away from the zone boundaries, then the perturbation has a very weak effect on the energy values, eigenvalues. So, basically the orange curve superimposes the free electron parabola unless you come too close to the zone boundary. Okay. So, to prove that, we'll prove that in a minute. So, if we pick a point, any point here, and call it Q, this is one of the allowed values of Q, allowed by the periodic boundary condition. I picked it here, right? So, you can draw a vertical line over here, and you can see that it cuts the dispersion at various places. So, this point here is EQ or QE, the x coordinate is Q and the y coordinate is E. Here again, the x coordinate is still Q, but which branch is this? So, if this point is Q, then if this point is Q, then my question is where will Q minus G be? G naught, let's say, G naught is 2 pi by A. G naught is the smallest reciprocal lattice factor. So, can you locate Q minus G naught? Right. So, minus G naught is here. This is minus G naught. And then you take Q away from it. So, you will land somewhere here. And this point maps to this and this maps to this. So, you can convince yourself that this point is essentially Q minus G naught. Got the logic? If Q is here, Q minus G is here, Q minus G's energy eigenvalue is here, and that maps to here. Okay? Good. So, now the energy at point Q with the perturbation on, this is the perturbation is H equals minus H bar square by 2m del square psi plus V psi, where V of x plus NA is equal to, we are dealing with 1D for simplicity. So, here you know what is A. A is the lattice spacing, right? So, let me draw it anyways. So, this is my lattice whose length is L. So, I can think of it as being extended from minus L by 2 to plus L by 2. That's the length of my, so it's a 1D box if you like, the electrons in 1D box. And this parabola corresponds to electron in 1D box without any ionic cores. But then you can start, you can have, of course, this is, in reality, this L is very large compared to A, which doesn't seem to be the case here. So, this is your lattice spacing A. So, if you have a total of, let's say, n lattice points, now you have to pay a slight bit of attention. Some people call it n unit cells, but they mean the same, right? Because in a Bravais lattice, each unit cell has exactly one lattice point, right? So you will, in many books, you will say unit cell. So a total of n lattice points or n unit cell. So what that means is that n times A is equal to L, right? And yesterday I showed you that if you have n electrons, then this band, the first band, so we also used nu as the notation for band index, indexing the bands. So the nu is 1 for this band. So if n is, if you have exactly 1 electron per unit cell, then the first band will be exactly half filled, and therefore this material will behave as a metal. And if n happens to be 2, then your band is completely filled, and there are forbidden states. The next accessible states are too far up in energy. So therefore, if you apply a modest electric field, the electrons would have no quantum state available to them to move, to carry the current. Okay, this may not make much sense to you at this moment, but once we will do transport, then things will start making sense. But don't worry about that. So now EQ is the energy in the perturbed state. So basically EQ refers to the orange curve over here, and E naught Q refers to the unperturbed or the free electron parabola. How are these two connected to each other? So they can be related to each other using the perturbation theory, because we are assuming that V is a weak potential, weak periodic potential that we have turned on, and we are looking at the effect of V on size and ease, okay, energy eigenvalues and eigenstates. So in the perturbative approach, EQ is equal to E naught Q plus the first order perturbation term, right? Do you remember what's the first order perturbation term? You take the eigenstates of the unperturbed state, right, and you calculate this quantity, this bracket, Q V Q, isn't it so? That's your first order perturbation. But I will show you in a minute that first order perturbation theory would do nothing to our free electron parabola. Okay, it wouldn't be very helpful to us. It wouldn't explain the gaps that we have opened up. So we'll have to go to the second order perturbation theory. So in the second order perturbation, you have to calculate these brackets. So mod of Q V Q prime, summing over Q primes. I will come to in a minute what is Q prime, divided by, remember, E naught Q minus E naught Q prime. Now what is Q and what is Q prime? Q is some point in the Brillouin zone, some allowed Q value. And what is Q prime? Rest of the Qs in the Brillouin zone. So you have to sum it over how many Qs? How many terms will be there in this? Maybe 10 to the power 10. As many as the number of Q points. And how many Q points do you have between minus pi by n plus pi by a? Huge, 2 pi by L, 2 pi by L or 2 pi by n a, right? That's the spacing between the Q points. So it's a large number. So, but you would see that, you would see that something will happen which will allow us to evaluate this sum rather easily. Otherwise, I wouldn't have been doing it here had it been a sum of 10 to the power 10 terms. Okay, now all of you are smart people, so I'll take your help. I'm really very, very bad with maths, but I have it written on this piece of paper. But I'm sure you guys are much better and much faster. So I'll need your help to evaluate this bracket, also call it a matrix element M Q Q prime, right. So, what would this be? So, what is the eigenstate Q? By the way, I didn't put not here. Ideally, I should, because these are all okay. Q's are Q's anyway. It doesn't matter. So, what is Q? Q is the eigenstate, which is basically psi 0 Q x, and which is basically 1 over root L exponential I Q x, a plane wave traveling along the x axis. That's what it is. So, if we then use this, and what is V? V is written over there. So, let's before coming to this, the next step would be that this matrix element would then be integral minus L by 2 to plus L by 2, then your psi star V psi d tau, in this case it will be dx. So, it will be basically e to the power minus I q x V e to the power I q prime x dx. Is it fine? Nothing wrong so far? Good. Now, this V, I was talking to you about this V because V is periodic and it has the periodicity of the lattice. We must take advantage of that, right. So, first of all, any periodic function can be Fourier expanded, right, and you can expand it in plane wave basis. Using sines and cosines, you can expand any periodic function. So, this is very normal. I mean, there is no magic in this. If I say that V can be written as summation over Q VQ e to the power I QX, isn't it so? I mean, e to the power I QX is the plane wave basis, and you have these are the Fourier components, right. Now, the thing is that because V has the periodicity of the lattice, therefore, the only Q's that are relevant to us are the G's. What I mean to say is that in this expansion, you just need to worry about this. This is my assertion. Can we prove it? You have to prove this as a homework problem. And you have to remember it throughout the course. This is very normal. This you do in every course. But this you do only in condensed matter physics dealing with crystalline solids, crystal lattices. Well, actually, I took this challenge of proving it, and I could do it. So, if I could do it, I am very, very sure that you would definitely do it. Correct. Yeah. So, this is just to be more explicit. This is V of x is equal to this. So, this is your V of x. I mean, I didn't prove it. Basically, what I did is, I'll give you a hint. I said that if V of x is this, then what should be V of x plus NA? Then I put replaced x by x plus NA, and I replaced G by 2 pi by A times M, and I got my Vx back. Because e to the power I times an integer would be 1, right. So, that is how I did it. But it's, I mean, I think you can find a more rigorous proof. You would do it. Good. So, with this in place, we just need to bring our Vx over here and then we are ready. So, let us do that. So, shall I erase this? So, or maybe we can just lift the board up. All right. So, here we go. For this V, we will write summation G Vg e to the power I Gx times exponential I q prime x dx. Okay. So, okay. Now, this guy is not very difficult to evaluate if you think of it. Summation over G can come out of the integration sign. So, is Vg is the Fourier component of your potential, and then what remains is just minus L by 2 exponential I times minus q plus G plus q prime x dx, right. Now, think of this integral. Have you seen this integral before? I showed not the integral, but a summation of this kind in the first module of this lecture, when we were trying to prove that the reciprocal lattice of a 1D lattice with lattice spacing A will be 2 pi by A. So, this integral is nothing but this, some lower limit, upper limit e to the power I alpha x dx. Isn't it so? Right? Do you know this integral? I am sure you know it. If I make this minus infinity and this is plus infinity, what then this integral is? Huh? It's a delta function, right? It's a delta function, right? And here L is in fact very large, right? So, for all practical purposes, this integral is a delta function, which means it will live only when alpha is 0, right? Isn't it? This is delta alpha modulo 2 pi if you are integrating from minus. So, what is delta alpha? Delta alpha is a function, is a function which spikes at alpha equal to 0 and elsewhere it is 0, isn't it so? So, therefore, this integral will survive, will see the light of the day, provided minus q plus g plus q prime is equal to 0. Or in another words, you can say that q minus q prime is equal to g. So, what have we achieved? We have achieved something really substantial. What we are saying is that in this summation, only those q primes are relevant that are related to my q using this relation. Other q points, there are many q points. We don't care about them. We only care about the q points that are related to my original q through this relation. And what is this relation, by the way? This is the familiar Laue condition. So, an electron in a state q can only scatter into a state q prime which is related to q by Laue's condition. Why? Because these are waves in a periodic lattice, right? This is the property of periodic lattices. Okay? So, we obtain something really remarkable, which is this, which is Lave's condition applied to electron waves in the periodic lattice. And it will certainly help us, it will save the day for us, because we will not have to now sum over all the Q points. But still, even though now, even though we have obtained this condition, how many sums will remain there? Can you guess? So, suppose you fix your Q, right? Then you get Q minus G, then you will get Q plus G, then you will get Q minus 2G plus G's, and so on and so forth. So, all the points that are along this line, which you draw vertically, cut the dispersion. Only those points are important. But you see that this EQ, this denominator, is the difference between the energies, right? And this difference is already pretty large for this pair. It will be even larger for the next pair, it will be even larger for the next pair. So, what is going to happen? Those terms are going to be smaller and smaller and smaller. Not just that, the other thing is that we have not yet completed this. So, let us first complete this, then I will come to the remaining point. Let us complete this. So, what did we get? So, if Q minus Q prime is equal to G, then this integral will survive, and what will remain? What will remain is just Vg, that particular G. So, suppose you say that this argument is 0 for some G. So, that component of your Fourier transform V will remain. So, this is what the matrix element is, M Q Q prime or Q prime Q, right. This matrix element, I have just named it like this. So, these are Fourier components, right. So, when G is G naught, you are dealing with the first Fourier component. When G is 2G naught, you are dealing with the second Fourier component, third Fourier component. So, in the first term, you will get the first Fourier component. In the second, and the energy difference will be this minus this. In the second term, you will get the second Fourier component sitting in the numerator, and in the denominator, you will get the bigger difference in energy. In the third term, you will get the third Fourier, right? You got the point, right? Now, if your potential is already weak, then your Fourier components, subsequent Fourier components are going to get smaller and smaller and smaller. So, therefore, we have second reason to not consider the higher order terms in this summation, right. Okay. So, let us now do it. So, what do we then get for EQ? EQ is E naught Q plus QVQ. So, what will be QVQ? Since we have evaluated QVQ prime, what will be QVQ? Who will answer this question? What will be QVQ? Yeah. If you put Q equal to Q prime, what will you get? 0. What is that? That is the DC component of your Fourier transformed potential, right. So, Vx has terms V naught plus Vg plus V2g plus V3g and so on and so forth, isn't it? I mean, when you Fourier transform. So, that is the DC component. So, that is just V0, that is the first term in the Fourier series. So, Q Vq is nothing but V at g equal to 0, which is V0. So, that is what I was telling you, that if you consider only the first order perturbation, then the effect of first order perturbation is to give a DC shift to the free electron parabola. That is not going to change anything for us. So, that perturbation is not very helpful. In fact, you can assume this to be 0. So, you are back to where you started. So, the second term is important, and what the second term will give you? The second term will give you mod V G naught square divided by this energy difference. So EQ minus EQ minus G. Then you go to the next term where you will get V 2G naught square divided by similar difference in energy, which is even bigger, and so on and so forth. So that's what you're going to do, right? So so finally where we are now? So what we say is that this term is anyways 0. These energy differences are anyways very large. This is large, this is even larger, the next one will be even larger. So even this term, this whole term, the third term in our expansion, is very small compared to E naught Q. So for all practical purposes, your EQ is equal to E naught Q. So we have not learned anything, seems. What we are saying is that EQ will be same as E naught Q, but there is a catch here. The point is that this whole thing, this expression will break down when E naught Q is equal to E naught Q prime. Isn't it so? Which means that the two states have the same energy, right? Q and Q prime have the same energy. And when will that happen? That will happen at this point. In the unperturbed system, at pi by A, your EQ prime and EQ will have the same energy. And that is where this approach will break down, right? So here the approach that we used is the approach that we typically use in non-degenerate situations, and the system is non-degenerate all over here except at this point. So at this point, this approximation will break down. So what have we learned so far before I go further? What we have learned so far is that for a very weak periodic potential, the free electron parabola and the perturbed energy Q dispersion is not going to look any different from each other except close to this. But at this point, what exactly the difference would be, we have not evaluated as yet, right? We have not done that calculation so far. All we have shown is that if you are away from degenerate point, this point, then orange and white, they are going to superimpose on each other. There will be small shift because of this term, right? And this shift will become more and more important as you will go towards the zone boundary, because when you are away from the zone boundary, this energy difference is large and it's getting larger and larger and larger. So therefore the denominator is very large, and therefore this term contributes very little. It starts contributing only when you come closer to the zone boundary, because this energy difference is diminishing, okay? But exactly at the zone boundary, this whole approach breaks down. So we cannot use this approach to see what will happen at the zone boundary, right? So for that, we have to change our approach. So what do we do then? And because the potential is real, by the way, so the Fourier component at G and minus G is going to be the same. But that's a side information, not very important. Now we go to the next part of our calculation, which is the calculation of E of Q at pi by A, which is where the expression 1 breaks down. The non-degenerate perturbation theory breaks down. So we can calculate EQ at pi by A using the degenerate perturbation theory. Perturbation theory. Okay. So let me write down the expression then for EQ, because these are very well established relations in quantum mechanics. I don't know if you have already done degenerate perturbation theory or not. If you have done it, then you will not have any difficulty whatsoever. But if you have not done it, then you will have to, take it with a pinch of salt. So it looks like this basically. So going back to the same notation which I used previously for the matrix element, MQ, Q, M, Q prime, Q prime divided by 2, and then plus minus under root M Q Q minus M Q prime whole square by 4 and plus, it's a long expression, let me erase this also, M Q prime whole square. This is the formula which I took from a book. Yeah. So if you can calculate these matrix elements, then you would have the energy at pi by a. So if you're calculating at pi by a, then Q is equal to Q prime is equal to pi by a. Right? So you just plug in here you have already obtained an expression. This is actually your MQ prime. So this again would be the V naught. This again would be V naught. V naught plus V naught by 2, that will be. So then let me write down. So you will have E naught at pi by a plus 2 V naught divided by 2, the DC component. So divided by 2, so 2 will get cancelled out, so you just get V naught. And here you will get a contribution only from this term. From this you get V naught, V naught minus V naught is 0, so that again goes away. You get only this, so you get, and with this you will get V G naught, where G naught is 2 pi by a. Remember, G naught is the smallest reciprocal lattice vector. Of course, same thing will be true for this point, but for this point you will have to consider your Q's and Q primes from these branches, not from, right? You got my point. So this is valid only for the energy at the point pi by a, or minus pi by a, plus minus pi by a. That's the expression for the energy. Now, plus corresponds to this branch and minus corresponds to this branch. Okay, so for one of the so here for one of the branches the energy will lower, and for another branch the energy will rise, and therefore you will get a gap. So this is what the gap is. So the gap value, therefore the energy gap, or the forbidden, where there are no electronic states, forbidden energy gap is equal to, so one state has gone down by an amount Vg naught, another has gone up by an amount Vg naught, so the gap is twice Vg naught. Right? And if you do it, if you use the same approach for this point, you will see that the gap will come out to be related to the second Fourier component, I believe. I don't remember now, but one can do that in the same way as we have done it here. So this is all about scattering. Yeah. Yeah. I mean, so far, by the way, in evaluating this, we have nowhere used that fact, nowhere used that approximation. Hmm. Huh. Huh. Sorry, say it slowly. You are saying that here we will get 2g naught if v 2g naught is greater than vg naught. Is that your point? No. So this term comes from this, right? And when q is equal to q prime, then you know that your g will be g naught, which means 2 pi by a, because that is when you get pi by a is equal to 2 pi by a minus pi by a. So q prime is equal to g minus q, the Laue condition. Okay. So I will erase this because we have to do one more thing today if the time permits. Sorry. 2 pi. Huh. Q prime. Q prime is this point, no? Q prime is this point. And when you are at the zone boundary, then both Q and Q prime are pi by A. Yeah? Now we go to the second part of this lecture, which is again which deals with something very important in condensed matter physics, and related to, of course, all that we are doing so far. And we will, in fact, we can do all this using an alternative approach, which we will generate now. So there is something in condensed matter physics that every condensed matter student should know, even non-condensed matter students should know. This is known as Bloch's theorem. I hope I have spelled it correctly. So this theorem was given by Felix Bloch, who won the Nobel Prize in Physics. I don't know which year, maybe in 1950. If I vaguely remember, it's 1952, and he won the Nobel Prize not only for this work, but not for this work, but for his contributions in the development of nuclear magnetic resonance spectroscopy. But you know, these are kind of people who didn't restrict themselves to doing one thing. So they contributed in very many ways. Bloch's theorem was one of his contributions, but I think his primary contribution is the development of NMR spectroscopy. And he was also the first general director of CERN. So high energy physics, someone who is doing class. Okay, so what is Bloch's theorem? Let's come to that. So in a solid where there is no lattice, a gas of electrons, we know that the wave function, which we have done so far, is simply I q dot r in 3D. Isn't it so? Now, real solids are not just free electron gas. The real solids are lattice, ionic cores, and the free electron and the electron gas. Free or not is another thing, right? So you have lattice also. So if the lattice, so this is without lattice, WO lattice, just a gas enclosed in a box, particle in a potential well, kind of. Now with lattice, in the presence of lattice, Bloch stated that this wave function is going to change as follows. It will still be a plane wave, but a plane wave which is modulated by a function which has the periodicity of the lattice. What that means is that you will have a function u qr times exponential I q dot r. Sorry, somewhere r is that way somewhere. That's what he said. He said that, you see, and this is actually essentially the property of the translational invariance, discrete translational invariance. When you go from one primitive cell to the next primitive cell, nothing changes in the real space, right? Then you go to the next primitive cell, right? So this function basically has or encapsulates within itself that essence, that property of the lattice, that from one unit cell to another unit cell nothing changes. So therefore, this function modulates with the periodicity of the lattice, changes with the periodicity of the lattice. So you have still a kind of plane wave, but plane wave which is modulated with this function. This function has the periodicity of the lattice, all right. Now this has very deep consequences if you think of it. What this means is that the electronic wave or the electron wave or the wave associated with an electron is extended all through the lattice by because it is essentially a plane wave which is modulated by this function, right. And well, I'm saying these things without proof, may or may not make sense to you, but this essentially has a consequence that if your lattice is perfectly periodic, then the electron will never ever get scattered, except of course when this Lave condition is met, and which happens at the zone boundaries, and then of course you form these standing waves. Otherwise the electrons are unscattered, and therefore from a perfectly periodic lattice you will not expect any scattering, and the mean free path of electrons can be infinitely large, meaning it will be limited only by the boundaries of the material of the sample, okay, that is called ballistic limit. However, whenever the lattice potential has an ambiguity, why should there be a problem with the lattice potential? There can be a problem with the lattice potential if you have impurities in your system, and no system is pure. Suppose you take a block of copper, you say it is 99.99% pure, but still you have 0.01% impurities. So in place of copper, at some places you may have manganese, or you may have iron, or you may have something else. So at that point the potential will deviate from its perfect periodicity. So there is a local distortion in the lattice, right, in the lattice potential, and that serves as a source of scattering, right. But that scattering is important only at very low temperatures. As you increase the temperature, the lattice doesn't remain static, it starts vibrating, right. You have done lattice waves, and these lattice waves actually, these are the ones that scatter electrons. So the resistance in a material is because of the lattice vibrations, because of the coupling between the electrons and the phonons, because of electron phonon scattering, right. That leads to resistance, that is the source of resistance. And what else is the source of resistance? The presence of impurities or defects in your crystal. This is the, so had your lattice being perfectly rigid, the electrons would not have suffered any collisions, and you would have a perfect superconductor at all temperatures. But because the lattice is not rigid, lattice vibrates, therefore these lattice vibrations, they scatter the electron waves, okay. But we'll come to that in the later part of this course. Now my intent is to prove this theorem first, and second, draw some general results from the structure of this wave function, right. So but those I will not do now because we are running short of time. However, I will note them down here for you to prove it. And I am telling you well in advance that this question is going to appear in the exam in one form or the other. So what you have to prove is, you have to prove number one, and because these are provable at your level very easily, that's why I am leaving it to you. First is that this function u, q, sorry, not u, q. First is that psi, this psi I am talking about, psi at q plus g is same as psi at any point q. Now in 3D, we have to put the vector notations. That's relation number one. Number two is that mod psi q r plus r whole square is equal to mod psi q r whole square. Where r is the lattice vector. That's number two. And a consequence of this is that energy at any point q plus g is same as energy at a point q. This, if you are looking at things in a extended zone scheme. Okay. So these are the things that you have to do yourself at home. One of these will come in the exam. Now, for the proof of this theorem, I think we will probably do it on maybe on Friday, because it's not very lengthy, but it requires some amount of focus, and I see that it's already 1 hour. So let's break here, and maybe then on Friday we will do the proof of this theorem, and the last lecture will be on what is known as the tight binding model, and then we will end this semester. So 2 more lectures basically, or maybe in one lecture I will cover both the Bloch's theorem as well as the tight binding model. Tight binding model is very important because that will give you the true sense of bands. So here we arrived at bands, at band picture from the free electron end. There we will arrive at the band picture from the other extreme, which is where the electrons are completely localized. They're orbiting around their nucleus, right? And from there, when you bring the atoms together, right, their orbitals overlap and the bands form. So from that picture, that is the essence of tight binding model. So we'll do that. So then you have now you have seen 2 extremes coming from free electron side, reaching the band picture, coming from the completely localized sides and reaching the band picture, right? That is the bare minimum we should do. The band theory is quite some, I mean, there are volumes written on band theory and there are very many methods. So we will not go into those details. Okay.